type of testing where we measure the DNL in all these different communities. Then we have portable noise monitors that can be deployed to residents or municipalities upon request. The residential deployments are 2 weeks, and then the municipal deployments are 3 months. We also do testing to determine eligibility for school sound installation. That's the third image you see. We also do laboratory and field testing of acoustical products, mainly windows and doors. The laboratory test is conducted before we install the products. That is to confirm that the products meet the specified requirements for sound transmission class ratings. And then we also, later in the field, when we install the products, we also test a sample of windows just to verify that those requirements are met. And today, we will be talking about this last type of testing, which is testing that's conducted to determine eligibility. A similar type of test will be also conducted after we install the product to confirm that the home has met the FAA's noise reduction goals. And Dustin will talk a bit more about this last item on the slide.
Donna, can I ask
Yes.
one question? To just clarify for anybody that it isn't exactly clear to. Previously, to qualify, you need only live within the noise contour.
That was one of the requirements. The home had to be located within the noise contour or block rounded.
Right.
And also it had to be built before a certain date, which was typically the date of the record of decision for that noise contour. And now we're introducing a third criterion, which is in addition to those two, the home has to be within the noise contour, block rounded. It also has to be built after a certain date, but now we also have to demonstrate that it meets or exceeds the 45 DNL interior noise.
And when you say we added this, who is we?
Well, we are the CDA is implementing these requirements, but the requirements are set forth by the FAA and are adopted nationwide for most residential sound installation programs throughout the nation.
It's a two-step requirement.
It used to be a 2-step requirement, now it's a 3-step requirement.
Three-step.
Yeah. So, and just a little bit to what we just touched on, the FAA came out with, to us at least, new guidelines that we are implementing at both O'Hare and Midway RSIPs. And this interior noise testing to determine the DNL is really the factor that's different from how things used to be done in the past. So, so today, in accordance to these FAA guidelines, we will have to be testing the homes, and again, Dustin is here to talk more about that. Thank you.
Good morning, everyone.
Morning.
So I'm going to start just quickly with the definition of an eligibility acoustical test, so you can kind of get an understanding of why we're doing this. So, as Donna mentioned, this is an in-home sound test. We're measuring how much noise is being reduced by the existing doors and windows and facades of the home as it sits right now. And the reason that we're doing this so that we can determine if that interior noise level is going to meet that FAA-defined threshold to justify the need for sound insulation in the home. So as we go through this today, there are really going to be 4 main topics that we're going to cover. Habitable room identification, the equipment that we use, how we conduct the measurements, and then once we have finished the measurements, how we use that information to perform the analysis. Knowing that this eligibility test is part of this determination of whether a home can be in or out, the FAA has put out this advisory circular, which is referenced here on the slide in 2022, which gives detailed instructions on how this is supposed to take place. They've standardized this across the nation by releasing this, and all the testing that we do will be in compliance with that. moving on to the first item here, we've got habitable room identification. For this, the FAA defines a habitable room as an area that's used for living, sleeping, eating, or cooking. And it also must meet all the local building code requirements. Some examples have been shown here for you, so you can kind of see how certain rooms might fall one way or the other. But generally, why is this important? There are two main reasons. So first, we've got that only the habitable rooms are going to be evaluated when we determine this eligibility of the home. We are not testing the non-habitable rooms. And then second, only the habitable rooms are going to receive the sound insulation treatments, which is very important. The goal is for the habitable rooms to receive the noise reduction. Kind of taking that one step further, when will the FAA allow us to treat a non-habitable room? The only instance really would be as if there is an open connection between a non-habitable room and an adjacent habitable room where we have a noise path for that to travel between. In those instances, they will allow us to treat that non-habitable room to eliminate that noise path. Next, we'd like to get into the actual equipment that we use for this. So before I do so, I want to just kind of lay out, there are two methods that you can perform an acoustical test per the FAA's advisory circular. The first is through what they call the overflight or the flyover method. And in this instance, we're actually using the aircraft as they fly over as the noise source for that test. The other way is what the FAA calls the exterior loudspeaker method, and that is what we use on the RSAP. This is where we're generating the noise manually. All right, so because we are generating that manually, we need to use a piece of equipment to do that. So the first item that we have here is called a signal generator. So Tommy, maybe you can just kind of hold that up. You guys can see it's a pretty small piece, but this is used to supply what we call pink noise. There's a broadband signal across a large section of the audible range. You may have heard of white noise, which is similar, but that's equal energy in each frequency. Pink noise is what the FAA asked us to use, and this is equal energy in each octave. If we can, we brought this here together. We'd like to give you a quick demonstration of what that might sound like. We won't turn it up too loud, but we'll let it go for 5-10 seconds, see what you guys. All right, so that pink noise signal is next fed into an equalizer. And we do this because the FAA has established a frequency band of interest for these acoustical tests. And that ranges between 100 hertz to 2500 hertz. We use this equalizer, and it's the top piece in our rack here. It has 31 bands, and basically what we're doing is we're taking that full spectrum pink noise signal, and we're breaking that down into 31 individual 1/3 octave bands. So we can raise and lower each of those octave bands individually as necessary. So our purpose for it is essentially knowing that the frequency band of interest is between 100 and 2500 hertz. Every frequency octave band that's below 100 hertz, we cut all the way down, and the same for everything above 2500 hertz. What this does is it allows us to have the strongest signal possible in that frequency band of interest. And since we're not concerned about taking measurements in those other bands, it kind of gives us a little more headroom in the system. Next, the signal out of the equalizer is fed into an amplifier. This is essentially just boosting that signal. So we're trying to get a level that's between 90 to about 105 decibels measured at flush to the facade exterior surface. So that's why the level that we're shooting to achieve. And then lastly, the loudspeaker is what's taking that signal and broadcasting it against the home. So for this, the loudspeaker is placed on the exterior of the home, facing at the exterior facade or of the habitable room that we're testing. There are specific things that we're looking at as far as where that speaker is to be. Generally, we look at a specific angle to that facade, a certain distance from that facade, as well as a specific height of the loudspeaker when it's aimed at that facade. As far as height specifically, there are really two heights that we go with typically for a first floor or a second floor room. We would have the speaker in a flat wedge position laying on the ground. ground. And then if we were testing a room that had an interior vaulted ceiling or a flat roof, or the measurement heights got to a point where we needed to be at least 24 feet off the ground, then we would elevate the speaker 10 feet in the air on a speaker stand for that. And then the last piece of equipment that we have here is the sound level meters that we use. So there are two of them. So Tommy has the interior system that we use, Jeff has the exterior there. Both of these are used simultaneously as the noise is being generated. So one person will be inside taking measurements, another person will be outside. Both of those sound level meters are meeting the type 1 standard for American National Standards Institute as asked by the FAA. And then the primary difference between these two is that the interior one is a much shorter extension pole. The outside one, we do need to be able to reach much longer distances, so we use that. Both systems are calibrated before and after every test that we do. We have a field calibrator that we take out with us to do that. And then we also do send both of the meters in on an annual basis for a third-party certification to make sure that it's meeting that type 1 certification. All right, so over to conducting measurements. So the FAA has developed multiple measurement procedures that we can use when we're testing different habitable rooms. Primarily, they're based on the unique situations that we find at each of these habitable rooms. So we could have rooms of different exterior facades. You might have 1 versus 2 or 3. You might have different measurement heights if we're in a larger building versus a smaller building, and you could also have different exterior accessibility just getting to the outside of the building. There might be fences, trees, things of that nature. So at the RSFP, we put together 3 acronyms here that are used for the different types of measurements that we would do. We have the 1W, which is generally just for a 1 facade wall, a room with only 1 exterior facade. The 2W1 would be for situations where we have a corner 2 facade room, but we can test that with only 1 loudspeaker location. And then the 2W2 would be for that same 2-corner 2 facade room, but there's some kind of obstruction, whether it be a fence, tree, something of that kind that's in the way, so we can't test that room with 1 speaker location. So we would actually need to do 2 separate speaker locations for that. The important part of this is that every room has its own specific speaker location and layout and configuration. So let's jump in a little bit more detail about those specific instances. So the 1W, this is an example and photo of a 1 facade room. We can come at this from the top side or the bottom side. It doesn't matter which direction we come at. It's based on accessibility, what can we reach. We would typically go at a 45-degree angle to that facade with the speaker, and roughly, in most cases, about 25 to 30 feet away from the wall itself. Here's an example of a 2W1. Here we've got 1 loudspeaker shooting directly at the corner of both of those facades. That gives us a 45-degree angle on both facades at the exact same time. And since there's nothing in the way, that 1 location can provide us even sound coverage across both facades at the same time. Lastly here, the 2W2. So here, hopefully you can see it in the image, but there's a pretty large tree right near the corner of the room that we'll be trying to do. We can't come at that with 1 speaker from the corner, so what we actually are doing is we're splitting the 2 facades into 2 separate tests. We would do 1 for facade 1 and a separate for facade 2. Right, so actually conducting the measurements, and we can give you a short demonstration of this as well. Starting with the interior, Tommy's got that there. He's going to kind of just demonstrate how we would take a measurement inside of a room. And I'll kind of narrate a little bit of what he's doing. So generally the main thing for the inside measurements is that the microphone is held at least about an arm's length away from his body at all times as he's making the movements. We're doing a 3D scan covering the interior volume of the space. So this is a pretty large space. We won't be able to do that here, but just for demonstration. And generally, he's trying to keep the microphone at least 2 feet away from the floor, wall, ceiling, any kind of hard reflective surfaces and this measurement will last 30 seconds. So then shifting over to the exterior, Jeff has our exterior set up here. Generally for this, we're gonna be selecting 6 points on the facade. He's gonna hold the microphone flush to the wall so that we've got that mic at least 1 inch to 1.5 inches away from the facade itself. And he's gonna leave it at each one of those points for about 10 seconds, pause the meter, move to the next spot until he's covered all 6 of those exterior points. If there are 2 facades, then you have 6 on one, 6 on another, so a total of 12 for that point. All of the fixed points that he's trying to pick are trying to maintain at least 2 feet away from any of the vertical or horizontal edges of that facade. And if we did have any kind of like an interior corner, say like if this was an interior corner here, you would want to be at least 4 feet away from that interior corner. Thank you guys.
Just a question. Did you guys ever consider that the plans are coming, they're above the houses? So the noise is really coming from top, not the, really, maybe some of it's coming to the sides, but you guys ever consider trying to get a reading from above the roof?
So for the speaker height, I think really kind of comes into play with situations like that where the FAA is asking us to raise it to 10 feet in the air when we have situations where we feel that the roof would be a contributing factor to that noise level in the room. So flat roofs, vaulted ceilings where you have less insulation value from above. And those are the situations where we elevate it. The speaker being on the ground is actually very intentional because there's a harmful reflection that's actually coming off of the ground and coming back up, which affects our measurements. So by putting it on the ground, it actually it minimizes the influence of that reflection. So for most measurements, that's the preferred location so that that influence isn't there.
Thank you.
For sure. All right, so analysis. So how do we take this information and how do we determine if a home is eligible? The FAA has given us formulas that we can use to do these calculations. I'm not, for the sake of time and just level here, I'm not gonna go into or show you those formulas on the slides, but they are in your printed packets at the end in the appendix, as well as references in the AC as far as where they came from. But what we will do is kind of walk you through just a quick overview of how we take the numbers and how we determine the eligibility from that. So here's a quick example of how we take the exterior and the interior numbers and we determine what the FAA calls noise reduction. Keep in mind that this is just, this is a 1 facade room example, and I'm only really showing you the 1,000 hertz calculation, but we would be doing this for each of the 15 1/3 octave bands that you find between 100 hertz and 2,500 hertz. But generally we have, in this case, say we have an exterior level of 90.6 dB, and then we measured an interior level of 50. What you're gonna see here is that for the exterior level, we're subtracting 6 dB from that measurement. There's a specific reason for that, in that our ultimate goal is to measure an exterior level that is in a free field environment. So we are measuring flush to the facade, so we're basically introducing a reflection off of that facade coming back to the microphone. This 6 dB adjustment is to account for that reflection that's coming off of that flush measurement situation. So here, if we were to subtract these two numbers, we would get a noise reduction of 34.6 decibels. And again, like we would do this 15 times for each of the 1/3 octave bands. Next here we have where we go to the next point is the noise level reduction. So in the white row there, you'll see each of the noise reduction values that we've calculated for each of the 15 1/3 octave bands. Above that, you have the exterior aircraft noise spectrum. There is more information on how that spectrum is developed in the appendix, but just for simplifying things for right now, it's generally the most frequently operated aircraft for the runway adjacent to a certain community.
Can you back up on that a little bit? That's a long sentence. You said these are fine-tuned for certain aircraft at certain runways for certain communities?
So what it is essentially is we look at what is the most frequently operated aircraft for the runway end that's adjacent to a community. So a lot of times that ends up being the same aircraft. It's not always going to be different for different runways, but whatever that aircraft is that has the most frequent operations, we would get the spectrum from AEDT, the modeling tool, FAA's modeling tool for what is the spectrum of this specific aircraft. There's a little bit more to it beyond that point. I really don't have time to get into all the specifics of it, but generally that's the concept.
Well,
is
we
what
could
is the most
discuss it
frequently
in another
operated
meeting, but I think anybody here would agree that there is no one aircraft that flies from a particular runway in a particular direction. I don't wanna use the word helter-skelter, but it is. You can get any aircraft in any location at any time. So, but we'll discuss it at some other time, thank you.
So our next step then is to take that extra aircraft noise spectrum and we subtract the noise reduction from it in each of those 1/3 octave bands. So the blue row here is you see the difference of those two values. And essentially what we do is we take all of the exterior levels between 100 and 2500, we energy average those together to give us the A-weighted total level for the exterior of 81 in this instance. Do the same for the blue row, which gives us the interior A-weighted total of 56.4, and then the noise level reduction is simply the difference of those two values. So in this case, it would be 24.6. All right, so now that we know what the noise level reduction is for the room, how does that work towards interior DNL? So for this, we're essentially using an equation that the FAA has provided where we take the exterior DNL of the home, according to what the FAA has approved for the noise contour model. We subtract the noise level reduction from our test from that value, which then gives us the interior DNL. This is very important because we're not actually out there taking 24-hour DNL measurements. This is how the interior DNL is calculated. It's exterior level minus noise level reduction provides interior DNL. So there's an example here shown for this bedroom. Essentially, if we had an exterior DNL of 70, if we took the NLR that we just calculated and subtract that, we get an interior DNL value of 45.4. So say we've done that for all of the habitable rooms in this home, or in an example home. And the blue box there gives you a quick demonstration of, say, 3 rooms in a home. Generally, what we're asked to do is to identify the median, not the average, but the median of that data set, each of those interior DNL values. And that median is what will determine whether the home is eligible or ineligible. So in this example here, we've got a kitchen, a living room, and a bedroom. The median of those 3 values would be 46.9. So essentially what the FAA is asking us to do is look and say, is that median interior DNL greater than or equal to 45? If it is, then that home will be considered eligible. If that median interior DNL is already below 45, that's when that home would be considered ineligible. And in addition to that, the bottom bullet there, just for clarity, the FAA does not allow us to round these values. So if it's 44.7, it's 44.7. So to wrap things up, just some key takeaways to consider things here. So the first here we have is that all the testing that we're going to be doing moving forward on according to the TAP-EA contour is going to be in agreement with these FAA requirements and these guidelines. Second, we are using the FAA's preferred exterior loudspeaker method of testing, which means that we are not required, or we're not dependent on these overflight operations as we're conducting the test. Third, only the habitable rooms are evaluated, and only the habitable rooms are treated. Fourthly, the interior DNL, like I said before, it's not a 24-hour measurement in the home. This is taking the exterior DNL from the FAA-approved noise contour model and subtracting the NLR from that room, giving you the interior DNL. Fifth here, we've got the median interior DNL being the number that we use when determining eligibility. And lastly, we are also doing post-construction acoustical testing following these same procedures, and that's to determine that we've met both of the FAA noise reduction goals, which are shown here. So thank you very much.
ask a
Question?
couple questions?
Sure, go ahead.
Okay, let's start back at the beginning. The noise generator using pink noise from 100 to 2,500 hertz. Has anyone shown or documented if that is relative to what the aircraft noise actually is? I mean, is there a correlation, is there a graph, a spectrum analysis printout that says that aircraft noise is between 100 and 2,500 hertz? Because human hearing goes up to 8,000 for average people and starts at 60 hertz. You could hear that, 60 or 120 for sure. So is there, and I'm not challenging your methodology. I'm questioning the FAA's methodology of putting these criteria down. So is there something that shows that the pink noise that you're using sounds anything like it? And there is no such thing as a typical aircraft.
Well, I would caution to say that we don't necessarily need the pink noise to sound like the aircraft noise, because we are not trying to mimic the aircraft noise when we're performing our test. All we're trying to do is generate a signal that is relatively flat across this frequency spectrum, and then determine what is the outside level and what's the inside level, so we could subtract the two. We don't necessarily need it to mimic the aircraft spectrum.
Well, have they determined that all frequencies penetrate drywall at the same efficiency?
I can't speak for the FAA as whether they have or haven't.
Well, again, I'm not questioning you, I'm questioning the criteria that they gave you to use. So on the one hand, you're testing from 100 to 2,500 cycles or hertz. But then on the other hand, for another part, you're saying you're measuring, you're trying to, I'm gonna use the word guess because the right word doesn't come to mind right now, but you're trying to figure out which aircraft is departing or arriving on which runway and how it affects which house. So on the one hand, you know, you're testing between 100 and 2,500 hertz, but there's planes that scream and there's planes that roar. Scream would be the high frequency, roar would be the low frequency. So if you're using just a general noise, but then on the other end, you're saying we only want to listen for a certain noise from a certain plane, it's like a disconnect between the tests.
Yeah, but you're still getting the decibel reading reduction.
Right.
So you should be okay.
No, because the 2,500 bothers me, the 2,500 limit. The planes make noise. I've done testing myself. I've printed out graphs of the noise that the planes generate, and they don't end at 2,500 hertz, okay? But we'll leave that one. Another thing is you don't measure reflected sound. If your house is out in Wayne on a 5-acre plot, then reflected sound is not an issue. If your house is in Chicago or any of the suburbs around here, you have a neighbor anywhere from 4 feet to 10 feet away. And the reflected sound should be taken into account because, if you're in between two buildings, you're gonna hear sound reflected from both of them. So why not take that into account when you're doing your measurements?
We do account for the reflection when we do a flush measurement with the 6 dB correction.
Well,
To
it
the
seems
extra
like you're
level.
doing a mathematical subtraction, an assumption.
This is direct from the AC. That's the exact number that we're asked to subtract when you do a flush measurement of that nature. And this goes back to several standards that preceded even this advisory circular as far as what subtraction should be applied when you're doing a measurement a certain distance from that reflective surface. So there's
And all
considerable
these-
research on that.
Now, all of these stipulations or instructions come from the FAA, right? Are these microphones omnidirectional or directional? Okay, we'll take the other stuff up at other meetings. Thank you.
Thank you.
Okay, next we have, the RSP odor mitigation phase 1. We're gonna get some information today. So Donna, is that for you?
Is it mitigation phase 1?
Yeah.
Then it would be me, yes.
Yes.
So, and just one thing, just related to the presentation, the CD is not going to make any guesses or any arbitrary